for showing up and sticking through the tribulations of us being banned from another popular streaming site. I'm going to start off really quickly by showing the old sample game. I believe I showed this in the very first demo, and we're just going to run it again for a second here. So we know what we're talking about. You know, it's going to get blown up. So that's got sound now, but other than that, it's essentially the same program as it's been for about, I don't know, since late 2014. Now, when I demoed it back then, one of the things I was demoing was this ability to run things in the compiler, right? That was one of the very first things that was neat about this language. And so here, we're still doing that, but I've changed the way that it happens. And one of the first things, actually the theme of today's demo, is that we're going to take that compile time execution and we're going to push it so much further than other languages do that it was already powerful before with what I've demoed before, but it's going to become so powerful that it kind of phase changes into something else. And that's pretty cool. So what do I mean by that? Well, let me just start with a simple example. You know, we've got some code here, as always, and we've got this thing that says hash run, and as if you weren't here for the earlier demo, you can go watch this explained in great detail, but this just at compile time will run any function. It's in the same programming language as what we compile, right? But we can run it at compile time, as opposed to the approach of a language like C++, where you have all this weird const expr stuff that is a whole separate parallel programming language or parallel language that you're only supposed to be able to use at compile time, and makes things very complicated, right? The approach here is to make things very simple. So one of the drawbacks to that, to the approach before, was that it felt like it would get messy with big programs. Like you just pile some compile time code in, and then you compile some release time code, and the compile time code compiles the release time code, and maybe some code is shared between both parts, but some is just in the compile time part and some is just in the release part, and you don't really want them to cross over. You definitely don't want your compile time thing to mess with the global state of your release program, because that would make it hard to predict. But generally also, you don't want to be putting functions into your release program that are only needed at compile time. For that and many other reasons, I made this abstraction called a workspace. And what a workspace is it's just a separate universe where code lives, and you can make several of them. And one of the things that that does for you is, first of all, it lets you keep things very separate. If you want to have compile time code be separate from runtime code, you can put them in separate workspaces, and they won't ever cross unless you deliberately cross them. But also, it means you can make multiple builds. So, you know, here, if I run this, it's just going to build one version of the program. You know, this is, I'm outputting a CPP file that I'm then invoking the Microsoft compiler on, right? And that's because we're building this release, right? But I can actually build two builds at a time in parallel. So if I run build all, I'm going to start a debug workspace, start a release workspace, and I'm going to build them both, and they will happen in parallel, right? So boom, boom. Now it looked kind of sequential there rather than parallel, but the main reason for that is because we're I/O bound, because we're outputting these. Almost all of that time is spent outputting these giant CPP files and then invoking the Microsoft compiler on it. Like our actual time to compile the code is very small. Anyway, and that's a issue that we would work around as we go toward implementing our own backend later, as opposed to compiling to C and then handing that off. Okay, so let's look at what this actually does. So I'm calling this thing called start a workspace, and what is that exactly? Well, you know, we take a name and then some function to set the parameters for the workspace. We create a workspace, right? And we call something called compiler begin intercept, which is a very interesting function that we're going to talk about later in great length. And then we call some procedure on the workspace that we passed, and that is the thing. If you look down here, we have setup, debug, and setup, release, and those are just the things that say, okay, this workspace has these build settings. It's debug, no line directives, here's the name of the output executable, right? And separate things for release, array bounds check is off and all that, right? So then we can build all of those at once. And so what this does is it gives us a very ordered process for creating many builds. In our game, The Witness, every time I want to update the Steam version, I need to make 4 different builds. If you work for a middleware vendor and you support a lot of different operating systems, then you have to make tons of builds, right? And right now, that's the kind of thing that you would have to use a makefile or many makefiles for, and part of my agenda is to reduce the amount of tool use. So, because a lot of tools are weird and they interoperate poorly, so if you can do everything from your main programming language, that's better. And so one of the things that you can do now is chain together as many builds as you want and execute them in parallel. Now, so far it's just like, okay, big deal. Why is that important? Why is he talking about this workspace abstraction? It just seems like a small thing. But it's actually a major deal because you could imagine your compile time code getting bigger and bigger until it's basically a large software suite of its own right. Like if you imagine something the size of Visual Studio, for example, being compile time code, you really want to be very clear that that's separate from your actual application that you're compiling. And this allows you to do that. And so as an example of this, I have put together this goofy thing. If you look at the top of this file, actually somebody, I forgot to put this in chat, but if somebody wants to put the URL to these source files so people could follow along if they're interested, just go ahead and paste that in there. So I've got this variable go bananas here, and if it's false, then I just do this very vanilla compiling. But I'm going to change go bananas to, actually, let's not do it that way. I could change it to true in the source file, but I could also do it here. I could say, the same thing as I did before, but say run go bananas equals true, because that's actually a mutable variable, right? It's colon equals. So I can set it, and I didn't spell it right. So let's do this, and that's not spelled right. So this is better than something like an ifdef because it's checked by the parser, right? If you spell it wrong, everything's good. So now we're going to go bananas and see what happens. Now, all this is compile time code right here. And we're playing music, and we're compiling procedures one at a time. And the procedures are sort of streaming in, and we're getting some kind of histogram about what's in our program, which seems interesting. I can actually toggle histogram between different modes here. This is the starting of some kind of simple IDE for watching what's going on in your program. I left the compile all on here now, so we're actually compiling both the debug and release builds right now. So now this histogram, let me wait till this completes, so we can actually look at the data without the histogram moving around. This should be done soon. Okay. And then we got the size of the executable, which is interesting. Like, how did it know that? That's the equivalent of a Visual Studio post-build step, for example, or something you might do at the end of your makefile is go stab the file, and we'll show how that happens soon. But anyway, so I have this histogram of every procedure in my program, right? The name is down here, and the file is down here, and I know the size. What that number is, measuring the size, we'll talk about. But so this is alphabetically, so things here on the left are A, and E, F, G, H, I, J, K, L, M, down to Z, right? So that's by name, which is this label up here, but I can right-click and go to by size. So now the biggest things in my program are here on the left, right? And the smaller things are on the right. So if I want to know what are the pigs in my program, I can see that instantly, right? By looking toward the left of the graph. Oh, the music is too loud. Sorry. Is that better? Yeah. Is the music better? Even quieter. Okay. Sorry, this is the fun of live streaming. All right. How's that, folks? Okay. So anyway, what I was saying is, you know, this is every procedure in my program, and I can see what the size is, and I can see where it is, right? Now, on this version of the graph, I can see what the biggest, piggiest parts of my program are. And here I can see them by file even. So every time this graph spikes up, it's a new file, right? And then within one of these little mini graphs, it's by size. So down here, you know, this is all the font code, and these are the heavier weight functions in the font code, and we go toward lighter weight. And that's the audio mixer, and that's another part of the audio mixer, two of them, and this is a print function. And over here, only this spike here is my main program, so that's interesting. And if you want to, you know, I put this together. This took me less than a day to put together. And I did it because people are always saying, hey, you know, at first when I started doing this, people were like, oh, it's impossible to make a new programming language. You can hardly even parse one. It's such a terrible problem. And I don't think that that's true. And then now that I've got that, people are saying, oh, IDEs and ecosystems, they're just so terrible. So I'm going to put together the beginning of an IDE. So already what's here is more responsive and interactive than something like Visual Studio. And I did it in less than a day. And it's playing music, which is nuts, right? I don't suggest that seriously. But anyway, so suppose I'm looking at my program and I want to know what the piggy things are. So like what is this print item to buffer that's the biggest thing in my program? I can just click on that and it talks to my editor, and now we're down in print item to buffer, right? And that's just a little 2-line hook. You could probably make it talk to any editor that knows how to talk to external programs. So I'm going to click around, like stop all music. What is that function? There it is. You see it on the bottom, right? Recompute page. Oh, look, that's the audio decompression, right? Fill sample buffer, that's part of the mixer, right? So you have this very nice random access to parts of your program, and you have a level of easy introspection on the size of things that you just don't even have with other systems, right? Now, the reason that I did this nutty thing where I'm playing music, you know, is like I don't think that you actually want your any actual software inspection system to play music like this. It's probably better as an internal program. But I wanted to do this to emphasize that none of this is actually in the compiler. Okay, this is all client code that I wrote in the programming language itself. So somehow my own code got all this information about what it's compiling. And that's what we're going to do the rest of today, is look at where this information comes from and how you can use it and what sorts of things you can do with it. Okay. So let me show you where this comes from. I'm going to sadly... Oh, and if you were thinking there for a second, like, oh, that sure took a long time to compile. What's the deal there? It's because it actually was rate limited. So let me, first of all, let me go back to just building one, just to make it clear. And then we'll go to bananas, right? So in order to create that visual effect, because I wanted to talk about how this information was streaming into the program, because that's going to be important later, I'm actually rate limiting this to only process one procedure at a time. So if I do up to like 1,000 at a time, you'll see we process the information much faster. So boom, it's already done, right? So I just wanted the cool effect of slowly building the histogram, but it's not necessary, actually. The compiler is much faster than that. Okay. So I kind of want to like change the colors and time to the music and stuff. It's fine. Okay. So let's look at where this comes from. When I turn on Go Bananas, whoops, can't type today. When I turn on Go Bananas, Oh, actually, most of that is in the checking for that variable is in the other file. Let's just look at this loop of what happens. Actually, you know what? Let's switch to a simpler program to look at the loop, because that'll be better. But the point that I wanted to make with this more complicated example was just that you could see how going from there, you could run quite sophisticated software at compile time. And so you need a way to be in control of a quite sophisticated program from within the compiler. And that is why I've done this architecture that I'm going to show next. You know, like somehow, like I said, I'm getting information about all these procedures, all these declarations, like things that are defined in the program. How am I getting that information? Well, the compiler gives it to me, obviously. How does the compiler give it to me? Well, the first thought that you might have is, well, maybe the compiler gives you a callback. Maybe it'll run one of those like run commands every time a new thing gets declared. Or maybe it'll run one just at the end after everything's compiled and like pass you this big gob of information. I didn't like either of those things because they're not that versatile. Especially callbacks, I don't think are a very good idea because callbacks are for little code. The bigger your program is and the more sophisticated you want it to be, the more you want to not be in a callback, the more you want to be the main program, which is why I showed that Go Bananas example, because it starts a couple of threads actually, right? It starts a UI thread so that the updating of the graphics won't be slowed down by the compilation, and it starts an audio thread so that the audio mixer, you know, never misses. And like starting threads from within a callback is kind of bad beans. So anyway, let me talk about what happened. Let's run a much smaller, simpler example. We'll go back to that bigger example later. But first, I'm going to just compile this. So I'm going to say test setup, right? So we're printing some CRCs that we're computing, and we've built some. Never remember if this lands in. Does it land in there? Yeah, 7:20 p.m. Okay. So I'm going to run this program, and then we're just going to look at the demo program and see what it does. You know, it just prints some things like usually. Like we've got some factorial functions. We're printing some strings and maybe some CRCs, okay, and then some strings and some numbers. So that's nothing too crazy. But let me point out one thing that happens. So here in setup, we've got some build routine, right? Build that we're going to look at in a bit, right? That's all this stuff. And then it calls a bunch of code. You'll notice we're like on line 800. So there's a bunch of code above here that we're using to build. But the thing that we're building, if you look here in our build routine, we're adding a build file, demo, right? So if you go to demo, this is the actual program that we're compiling. It's in a different workspace. And it has its own compile time things that it runs. So for example, we've got some strings here. We're calling this function initting strings. So when we compiled, right, we said initting strings, and we computed some CRCs, right? CRC is a cyclical redundancy check. I think that's what the acronym stands for. And we're computing those. So we've got a function that computes a CRC of a string, and then we're setting those into a global table. Now, one thing that you might think to do if you want to pre-compute some global variables is, and I've demoed this in previous demos, you could figure out the values, like figure out the CRCs of these strings, and then print them out into a string that you insert into the program, right? And then you parse that string later on, and that gives you the values of the variables at compile time, right? And you can do that. That's like a more straightforward version of what you might even do in C++, where you have, you know, some external program that generates text file that you include or something. But you know, I was thinking, once you have the clarity of these workspaces, why not just eliminate the middleman, right? And just put the values in the table. Because once you've got workspaces and the target code is clean and separate from everything, why can't you just store variables in the globals, right? Why do you have to like put them in as a string? That's like extra busy work that you shouldn't need to do. So here's what we do. We call make prehash on piece A, which is just this string by itself, and piece B, which is this string by itself. And then we do versions where we concatenate them in both orders, right? And we fill out this prehash table. And that prehash table just has the name as a string in one slot and then a CRC in another slot. And that's it. And that's all we do. This run command runs this at compile time. And then at runtime, we just have these values, right? Because when we get written out with the values of these global variables after this has run, right? That used to not be true. Before I introduced workspaces, for clarity purposes, I just always reinitialized your globals to 0 or whatever their default values were. But it seems better to do this because I think you can do pre-computed things much simpler and more straightforwardly. So you can see the main program that's running here. First, we do some math stuff, which is what's printing those factorials, right? And then we print out these prehashes here, right? And that's just this loop. So we haven't initialized them. We're just printing the values that are in the global space, and they're already initialized. If this printout looks fun, oh, and you'll notice these CRCs are the same ones that we computed at compile time, right? That 7VK, SO18, etc. Now, if this looks funny to you, it's because it's in base 64. We're printing things in base 64 because once you get to 64 bits, printing things in hex is a little cumbersome. So, we have a base 64, which is just numbers, upper and lowercase letters, and dot and underscore. And the compiler doesn't do this yet, but the plan is to make those parse as literals. So you could do like 0s or I don't know, something like that, and then a base 64 number. Okay. Oh, it's also worth pointing out that strings, a string actually, especially in this case, these strings are dynamically allocated. So there's actually special handling in the thing that puts your code into the target file that actually duplicates the string and puts it into statically allocated space. And I don't do that for arbitrary data structures yet. It's an open question about what. Like if you get into deep copying arbitrary pointers, then maybe you're in trouble. So I didn't want to do that. But simple literals that are native things in the language, it seemed to me like it made sense to support. So you can put a dynamically allocated string here at compile time, and it'll become a statically allocated string at runtime in your program. Okay. Now, let's go to the next example. So let's talk about how all this actually works in this simpler program. So we're back in the compile time program that compiles our stuff. We're running this procedure called build, and let's look at what it does. First, we set our own build options that we have no executable, right? This is our way of saying this workspace doesn't build anything, it's just compile time code. And then we set up another workspace, right? We created it here, and we say, oh, that's the demo, it's got executable name demo, and we update the build options for that workspace, right? We add a demo file, and then again, here's this compiler begin intercept. And what that does is it tells the compiler, hey, so far, you've been running little hash run commands on the side, sort of in the way C++ or D or those languages run them, where they're expected to be just mostly small expressions, right? And sort of the compiler is the main program, and the thing that's being run is a side thing. But compiler begin intercept turns that situation around. Here you're saying, hey, compiler, I am now the main program, and I'm going to interface with you more like a library, right? So I have flow control. I control everything, and I'm just going to ask you to update, right? So you're switching the role of the compiler and the running program. So then, after we do that, we go into this infinite loop, and we start asking the compiler for messages. If anyone's done message loop programming in something like Windows, this might look very familiar, right? If there's not a message ready, we can continue. I probably should have put a sleep in here, but I didn't. So this will just burn CPU until a message is available, right? If the message is, now remember there's two workspaces. There's the one for the compile time code and the one for the demo. And we're saying if it's not the workspace for the demo, then just continue. We don't care about that message, right? Now, what kind of messages are there? Well, all sorts of things that gives you information about your program. And now we'll take a look at what those are. And we're going to do that by turning on these options one at a time. So I'm going to turn on this doing build steps, and that's going to call this build steps routine, and we'll see what happens. So dash run, doing build steps equals true. Whoops, I ran the wrong thing. I ran the runtime for S doesn't make sense. I want to run this. Tests. All right. Notice that it's doing the same stuff that it did before, but it's doing some maybe stuff that's happening during the build. It's telling me about all the source files that are being opened and closed as the compiler works on them, right? So we start out with the demo, and the demo imports some modules. So it imported basic, which we open and close, and imported print and sort and math and CRC, right? And this is very valuable because in big projects, suddenly it can start to be confusing even what files are in the project, right? Like what is our compiled code pulling in? Because even if you use something like Visual Studio to organize things, you might have files listed in Visual Studio that aren't really necessary. You might have things not listed in Visual Studio, but that are somehow being pulled in, right? So this makes it very easy anytime you want to audit exactly what's going into your program, right, in terms of source files. Then we did all the stuff that we were doing before. And now, before we write out the executable, we are statting the file. So we're looking at how big it is, right? And then we're writing it. And after we write it, we're looking at how big it is again. Now, it's the same size both times because we just recompiled the same thing. It's got different CRCs, I think, because Visual Studio changes the binary a little bit. But if I go into the demo and I do something like the program should now be bigger, right? And I'm just going to make it a lot bigger. Oh wait, that's init strings. That's compile time code. Let's put it down in main, right? Now I have to apologize for this demo.cpp breaking this line here, but that's actually printed by Microsoft C compiler, and there's no way to tell it not to print that without like forking a separate console. And I don't know. I didn't want to get into that. So you should read this line as pre-write executable file testdemo.exe is blah blah blah, right? Okay, so we're going to do that again. We're going to run the build steps again, and we should see that the old file size is this, but the new file size should end up bigger. And it did. So you'll see, right? 112.160, right? Or 6112.8160. So that's cool. So you can imagine all sorts of, many uses for this. Let's look at how that actually comes about. We're going back over here. So remember, if doing build steps is true, which we turned on, we call this build steps function. And here's what it does. It takes this message that the compiler gave to us about what's happening, and it decodes it. We'll look at what the message types are in a second. But basically, if it's a file message, right, we can cast it to some struct that gives us information about what file the compiler is operating on. And if it's a compilation phase message, right, that gives us messages about what phase of compilation we're in. So we could be parsing source code, and then when all the source code is done, we get a message. When all the target code is built, we get a message. And before and after we write the executable, we get messages, right? So we can do things anytime we want in the middle of all of this stuff without going into the annoyance of per platform pre-build steps and post-build steps and middle build steps and whatever. You just write the program to do what you need it to do, right, as you intercept these messages. Let's look for a second in modules, compiler, and here are the messages that we get. Here's what compiler message file looks like, right? It gives us the name of the file and the path and whether we're opening or closing, right? Compilation phase message. We'll look at some of these other ones in a little bit. Okay. Now let's, another message that we can get is this code type checked message. And we get one of these every single time a top-level declaration gets compiled, or in the middle of compilation, right? After it's been type checked and known to be correct, but before code is generated. And that's because that's the time that gives us the most information, but while we could still change things, right? We may add other places to intercept code, but for now it's right at that point. And we have a thing here. If we turn on doing stats, So let's try that. I'm going to turn off doing build steps because that generated a lot of things. So doing stats is now true. And look at this. We get information. It's more like a textual version of what we got in that demo that we just gave, right? So here's the size of all our procedures by expression count. And I'll show you where that expression count comes from in a second. But we've just ranked them and listed them. So this is very useful. And then we get more information than just how big it is. We get all the information, and I'll show you what all the information means in a second. But for example, if you have a function and it's polymorphic, right, which is our version of C++ templates if you're a C++ person, then you know who it's polymorphic from. So down here I have a polymorphic function report where here are the functions that are used the most. Here's how many times they're used, right? And here's how big they are in total, right? So the total number of instances of different types times the number of expressions in one instance, right? And this is always interesting to see because, you know, sometimes it's unexpected. Like you might think, oh, I call array add, right? If I go into basic, if I go into array add, you might realize that that's a polymorphic routine and that it's getting duplicated anytime you use it on substantially different types. But you might think, oh, it's no big deal because it's a very small, simple thing that can be inlined or whatever. But you might forget that it calls reserve, right? And reserve is actually this bigger function that does allocation and expanding of the array. And that's actually the big hog, is the function that you don't call directly and that you don't think about, right? That gets automatically generated as a consequence of you calling array add. So code bloat is a very real thing. And you've seen in previous demos some of my other ways of attacking code bloat, for example, with the modify procs. But this is another good way to do it, is of just readily providing to you the information of what is happening with your code. And again, this textual version is very simple, but if you want the more graphical version, that whole go bananas thing will probably evolve into something that gives you all kinds of reports about what's happening. Okay, now I said that this actually gives you more information than we showed so far. So let me show you what that information is. Let's go back to the setup and let's look at the source code for this next one before we run it. Oh no, let's look at, okay, doing casts. Let's do doing scheme first, just because it's such a fun one. All right. So I'm going to turn on doing scheme, and that calls this function translate to scheme on everything in the program. Scheme is a different programming language, right? It's a language much like Lisp. It's a simplified version of Lisp, right? It's got this parentheses syntax. It's a prefix notation. It's a very different syntax. But I can actually compile or convert our demo program from this language into Scheme or into some other language like C++ if I want. Or if you're on a game and you're working on shaders, you could actually have a reference shader that's just in this language. And then you could compile it into GLSL or whatever the metal shader format is or whatever, because there's like 19 different shader languages right now, and it's crazy trying to deal with them all. So here's what we do. If we get a code type checked message, we check and see if it's in the file we care about, right? And if it is, then we call this print expression thing, and we'll just start looking at that. Basically, it casts it to something called a code node, which we'll look at, and it looks at what kind of thing that is. Is it a block? Is it a literal? Is it an identifier? Is it a statement? Is it an operator, right? Depending on what that is, we print out different stuff. Now, let me just show you the output of that. Boom. So this is our program in a different language, effectively. I was a little bit lazy and didn't totally do all the work, but let's just look at it for a second. So we'll go into demo, and we're going to look at main, right? So here it is here. We call math stuff, and we print this, and we iterate over prehashes and stuff. And here's the same thing in this prefix, Lispy notation. And I decided in this version of Scheme that you don't have to open a new scope when you say let. This is my version of Scheme with declare anywhere, because I didn't like the cascading indentation that would happen. right? So that's pretty cool because you can actually feel safe about forward compatibility of your code. Once it's in this language, you can put it into any language with relatively small amount of work, much less than it would be in any other programming language. You guys who have watched the live streams have seen, I have a large library of code in C++, and whenever I bring it over here, it's very ugly, like there's a bunch of macros and whatever, but this is very simple because this code here, I didn't have to parse it. The compiler parsed it for me. It handed me a parsed version of the code that's already in tree form and said, here you go. And I just had to write the output. And the output is pretty simple, right? It's a couple hundred lines for this simple syntax. So that's a very nice and very powerful thing. Let's look for a second at what that code node was. It's this sort of hierarchy of things. Whoops. It's in compiler. If you look in that, it's in module/compiler. So here we've got this enum called kind, which is basically every kind of node in the syntax tree of the language, like struct declarations or procedures, or a new or delete statement, or a size of or a type info, anything, right? A literal, which is something like a number or a string. And each of these is associated with another struct that gives you further information, which is how we were able to print out all this stuff. Like a procedure call. If you get procedure call in here, there's a struct that tells you what the arguments were of the procedure, which is why we're able to, for example, convert this call to the print function into a thing that shows its arguments. Now, let's actually look at that. So you can cast, if the kind is set to procedure call, you can cast your code node to a code procedure, right? Code node is the base struct. And then you get the block of instructions in the procedure. You get the block of types. You get an array of declarations of the arguments and the return values. You get the name of the procedure. You get the header declaration. You get who it's polymorphed from, which is how we were able to list that polymorph report. And you're able to get flags, which right now is just, is this foreign? Like, is this procedure declared in C, and are we calling out to it, or is it native to us, right? So all of this is very useful. And someone asked, this compiler gives you its internal functionality of the parser? Yes, that is exactly what's happening. And the type checker, because you know all the types of everything by the time you get this. However, it is also playing it safe, because what is listed in this file, this code, whatever, is not actually the internal representation that the compiler uses of all this stuff. The compiler explicitly exports all this in a copy operation. So this format can stay stable while the internal implementation details of the compiler change. So that is very useful as a long-term thing, right? This isn't, you're not going to have to change your client code every time I change an implementation decision in the compiler. There's a mapping that keeps it consistent. So you can see, like a declaration. Oh, well, okay, this is interesting. I'm going to pause for a second and get some more water. I'll be back in like 1 minute or less. Hold on. You know what? I think I forgot to hit the record locally button. So I hope Hitbox, God damn it, I hope Hitbox is recording this. I turned on save videos. Okay, we're going to record everything from here on. But I forgot to start local recording. Okay. Now, what was I going to do next? Okay, so that was a scheme conversion, but let's look at a simpler thing, a simpler way that you can use this stuff. So let's look at this doing casts. So right now, that was a use of this exported syntax tree information to convert the program, but you can do other things. For example, you can check the program for errors, right? Or for things that you want to look for that maybe other people don't care about, or the people who made the compiler don't care about, right? So let's look at one such thing. Doing casts, right? I call this function detect implicit casts. So there are some implicit casts in the language. In general, this language is much safer than C or C++ in terms of automatically coercing values, right? We don't allow most of them, but there are a few we do allow. And one that I allowed newly that used to be prohibited in every demo before this is like a multiplication or a division between a float and integer, right? As explained in this comment, if you're being very, very strict, you wouldn't allow that because you can lose information in some cases if the integer and the float are of weird magnitudes. However, it's a giant pain in the butt to have to manually cast those all the time, as I found when I was writing the code, and or when I was porting code over from C++. And I started inserting casts in all those places, and it not only annoyed me as a programmer, but it made the program more noisy. Because I want a cast to be a serious thing, right? I want to know that a cast is important and signifies something major. And if over half of casts are just litter like this to deal with float int, that's maybe not so great. So as a compiler author, I made the decision, you know what, that is going to be allowed. Now, we don't actually allow it in other cases, like you can't pass an int to a function that wants float, for example. But in this particular case, it is allowed. But suppose now you, at your software shop, make very complicated software, and this is a problem that you run into all the time. At least maybe in certain subsystems, you might not like the fact that people could multiply this without a warning or an error, right? So you can detect that yourself. So here's what we do. Every time a message comes in, we check, is it a code type checked message? If not, bail, because we don't care. We cast it up to this code type checked type, and we look at the declaration. This tells us what top-level declaration in the program has just finished being type checked. A declaration is anything like a variable or a procedure declaration, etc. Constants, you get this message. So now, typically, even if you did have access to the syntax tree somehow, it would be some kind of like very complicated recursive structure, and you would need to use like a wacky visitor pattern to inspect that. But we do not require this because, whoops, I keep going to the wrong file. Because what we actually do, so we give you the tree, here's the root expression, you know, say that was a block. If you look at block, it's got like some statements and whatever, so you can recursively visit if you want. But we do that for you in the compiler before passing the message, and we flatten it. So there's just this array of expressions. So for example, if this is a procedure, and it's got some cast operation, that cast operation is somewhere in this tree, but it gets flattened into this array. So if I want to look for a cast, all I have to do is linearly iterate over this one array and say, is that cast in there? This is important. You're going to see this happen all the time in the following examples. It makes your code much simpler when you're writing this kind of thing. So I just iterate over all the expressions in the declaration. Is it a cast expression? No, then continue. We don't care. Okay, it's a cast. Is it an implicit cast? Well, there's a flag that tells us that. If it's not an implicit cast, bail. We don't care. All right, if it is an implicit cast, is it one that we don't want to happen? Because there are very legitimate implicit casts, like unsigned 16-bit to unsigned 32-bit number, right? You probably want that to happen. You could block that here if you didn't want to. But if it's an implicit cast between float and integer, we will complain about it. We'll say, hey, now, do you really want to do that? So let's run that for a second. Oops, that's my OBS window. So I'm going to run doing casts equals true. And now you'll see it detects all these places where we're doing implicit casts, mostly in libraries like the audio mixer. That was actually what was driving me nuts. We have a few in the demo. And if I want to be pedantic about this, of course, I have a way in the compiler of reporting an error in the standard format. So this function compiler report error, I pass it the file name, line number, character number in the message, and it gives me an error on the first one. Boom! You are not allowed to do that. So according to my taste, right, I can decide that this is a problem or not, basically at the same level of authority as the compiler. I have complete information, right? If you were going to write some program locally or studio that tries to search through all your code to like detect things like this, that might be very difficult because you have to parse the code, or you have to like make it use LLVM or something, and you have to set up the build environment to be the same as it actually is in production. Giant pain in the ass, right? Here, you just add a little hook into your regular build routine. The compiler gives you the complete information about what's happening. And in fact, this thing would be very difficult to search for syntactically because implicit casts are invisible. They're not represented by any syntax in your program, which is why I picked this case. Because you can't discover it just by searching your program text, right? You have to have full semantic knowledge of what your program is doing. So that's cool. Okay. Now, let's say you wanted to get even more hardcore about that. You know, sometimes I say, hey, this is a programming language for games, but what about other disciplines? You know, games shouldn't be taken to mean that this isn't a serious language. Games are actually some of the hardest software to write. Let's say you're in the automotive industry, and you have this body of standards called MISRA-C, for example. I guess they called it that because the rules make them miserable. I don't know. But it's called MISRA-C, and it's this rule book of like what you're not allowed to do, right? And what you're advised against doing. And just to show the capability here, I implemented a few of the specific rules out of that rule book, right? So here's our function MISRA checks that we call if we say doing MISRA is true. And this is quite more substantial than our previous implicit cast check. But for example, so we're going to restrict what we're looking at to just our demo file, right? I'm not going to search the libraries because they have some violations of these rules as well. Because, for example, you're not allowed to have recursion in MISRA, right? You're not allowed to do floating point exact comparisons, and you're not allowed to use pointers that are too scary. So I'm just going to turn this on, and we're going to start running it and see what it complains about, right? So let's say tomorrow I give up games and I get a job at an auto manufacturer, and suddenly my compiler starts complaining to me due to this code, hey, we've got a MISRA check failure. Functions cannot call themselves either directly or indirectly. Demo line 92. Oh, I've got this function that does Sierpinski curve, right? And that's a mathematical thing that's usually defined by recursion. And we've got this thing where Sierp A calls Sierp A. And let's say we just wanted to mess up our Sierpinski curve and get rid of the direct recursion, right? And maybe I can fool it, right, by just taking out the Sierp C and Sierp D. So I'll have this gimpy curve, but maybe it'll still work because I'm not directly calling each function from itself anymore, and maybe I can trick that. Which is why, again, if you were searching for something syntactically in like a build checking tool, you might not be able to detect the situation where A calls B and B calls A, right? That's a complicated situation that's much harder to detect, and actually we detect it instantly, right? Now it's not at line 92, now it's giving me line 142 is the first one. Oh, actually, never mind. Because we've got another example of direct recursion, it's complaining about that first. So here's a factorial. Fortunately, we've got a factorial iterative that we can use instead, right? So this is a recursive version that you use in computer science class. Here's one that just iterates, right? Oh, it's gonna... Did I break my recursive function checking? Ooh, I might have... It's supposed to detect the situation. Let's go through the other errors and let's see if I didn't break something. Anyway, line 207, floating point expressions. So let's check that one, right? So here's a case where I've got two floats. They're float 64s, and I'm saying it's F equal to G. And you really should never do that unless you exactly know that they hold certain bit patterns. Even if you're comparing against 0, you could have like a -0 compared against a +0 or something. So what you're supposed to do if you make cars or spaceships is you're supposed to have like an epsilon where you know that two numbers within that are roughly the same, and you do this comparison explicitly, right? And once I enable that, we're going to avoid that comparison, right? And then we've got this problem at line 217. Declaration of objects should contain no more than 2 levels of pointer indirection. Again, this is something that you probably want full semantics for because, okay, so we've got a float 64. We've got a pointer to it, right? That's not, it's complaining about line 217, which is the third pointer, basically, right? So we've got a pointer to it. We've got a pointer to that, so that's 2 levels of indirection. Now we've got a pointer with 3 levels of indirection, and Misra says that's crazy talk. You should never do that. So if we comment out C, we'll run fine. Okay, I refactored the code to scoot around the checking, which is why it didn't complain about the rest of the Sierpinski curve, but I didn't really break it. So now it's complaining about the indirect recursion. So now I'll show you how it detects this, but it's complaining about indirectly now that A calls B and B calls A, right? To get rid of that, we're just not allowed to have a Sierpinski curve in automotive applications unless we figure out an iterative way to do it or some other way, right? So, okay, so now we compile. So I've got this debug printout, right? It's call graph post check, and I'll show you what that is. So basically, in the Misra checks, the reason why it errored direct recursion right away is that I checked for that right away. So let's look for add to Misra call graph. I build a call graph at compile time of my program because I can tell who calls who because I'm given all that information in the declaration, right? And I'm organizing them by identifiers, right? So I've got like some hash table that maps identifiers. Is it a hash table or maybe it's just an array? I forget because I didn't care if it was fast. But yeah, it's just an array for now. So I have a table, flat array, that goes from identifier to some record of who that procedure calls, right? But I don't even have to do any of that check. If I see something that calls itself, right, which is what header equals target, right? Okay, so I should have explained this. Let me go to something for those of you who might be finding this harder to follow along. Like when I have something like factorial, right, and there's a function call, you get a node that says procedure call, and the procedure expression is a pointer on there, and that'll say identifier in this case. It'll say identifier called factorial. But it'll also tell me, it's not just an identifier called factorial, but it'll tell me, because we're already type checked, who that identifier resolves to. It'll tell me that identifier resolves to this. So when we look here, we got an identifier. We look at the resolve declaration. If that target resolve declaration is the same as the header of this declaration, that means this function is calling itself, so we're going to complain about it. And that's why those were caught immediately. Now, if they're not the same, then we go down to adding it to this call graph, right? And we just keep adding functions to this call graph. And then the post check, which you saw the debugging printouts there, which are generated here, after your whole program is compiled, it then iterates over the call graph and does this thing where it merges the information from call graphs together. So if A calls B and B calls C, then we put C into A's call record and so on, and we keep telescoping them down until you get effectively A calls A, right? Once you get that, then you can give an error, but it requires, you know, some number of steps, which is why we have this while changed. We set change to false, and then if we ever get new information about who calls who, we set change to true, and then as soon as we get no new changes, we break out. So I've done something quite sophisticated in there as a check at compile time. I'm trying to use the word procedure to mean what it really should mean, right? I have a bad habit from C and C++ of calling something a function, but in C and C++, function actually means procedure, and I'm trying to get into the habit of saying procedure because the difference between a procedure and a function is very important, actually, because functions don't have side effects and stuff. Well, and you know, a function is basically what math people mean when they say function. So I might mistakenly say function sometimes, however. Okay. Now, okay, so that's auto industry. I don't work in the auto industry, but I just wanted to show that you can actually get very hardcore about inspecting your program for problems. Now, the place where I'm interested in that kind of thing happening is in games, because we build very complicated games. The games have big code bases. They use external code. They use our own code. They do threading and all sorts of complicated threading. So another example, or a thing that happens to me all the time, is as my code that's threaded gets bigger and bigger, my morale about that code goes down. Like, I don't know exactly what's in there, and I don't really know what it's doing. And even if I'm just one programmer on the project, I might insert something into that ostensibly thread-safe code that breaks thread safety because maybe I didn't realize it has to be thread-safe, or I wasn't thinking that hard about it. Or maybe a new programmer comes on the team and they don't realize that they have to treat that file with kid gloves, right? So I have a thing for thread safety check that's, it doesn't analytically check for thread safety because that is impossible. However, it's just doing a simple thing that helps, and I'll show you what it's doing. And in fact, it's been running this whole time. So we're calling this routine thread safety check. And what that does is it just says, I'm allowed to have certain files that are basically like thread safety zones, where those files are, whoops, I left a debugging printout in here. Those files really are supposed to be self-contained and not really call very much outside themselves, right? Because we're supposed to be very careful about what goes in that file, because that file maybe runs from all kinds of contexts, and if you do something not thread safe in there, it's bad, right? So an example of what has to be thread safe is the audio mixer. So let me go into modules. So mixer is this main program for the mixer, and it does all sorts of interfacing with the state of the world or with whoever's interacting with it. And it's got all these entry points, right? And this, it takes locks. It is not generally, it's thread safe in the sense that it has all these locks and stuff, right? I'm trying to figure out the best way to explain this. It's a very heavyweight, front end to things, but it's a front end for talking to the thing that actually mixes the audio sampler, which runs very quickly in the background in an asynchronous thread. So this thing, passes data to that guy via interfaces that we have to be careful with, right? Now the async part is just running all the time in a separate thread, and the main program doesn't talk to it directly at all, except through that interface. And so this is a program where you have to be careful, right? If you, for some reason, started reading a global variable, I said local, but I mean global. If you started reading a global variable that was somewhere else in the program from here that's not carefully audited and thought about, that global variable might change while you're processing audio samples, and it might cause you to do something bad, right? That's a classic hard to detect thread safety bug. Now, I may need to read some globals. So for example, here I've got some global variables that I want to read. They're contained in this file though, right? So like I said, this thread safety check has been going this whole time. I don't need to turn it to true because it is true. If I just go to vanilla setup, it's passing. No alarms are going off. But suppose the new programmer on the team came and said, oh, I want to call math stuff and I want to set some variables from inside this function. This function is some asynchronous audio thing that's just cranking, right? And so what happens is my check will complain. It'll say, hey, math stuff may violate thread safety. It refers to something in a different file than the one where it is, right? So again, what we're doing is we're detecting that there's an identifier in this thing, and it's calling out to another file, and that is not allowed except in certain cases, and I'll show you what those are, right? So I can comment that out. It'll complain about the next line because we don't just care about functions, we care about anything, right? Oh, this identifier prehashes may violate thread safety because, we're doing something here that sets something. So that's no good. If I comment that out, we'll pass thread safety again. So this is a very good way for alarm bells to go off if somebody does something dangerous. Now the important point here is these are not like standard practices that the C++ committee can tell you or that we can build into the compiler necessarily, because these are custom to my code base. It's like we want to have a certain way or certain kind of things that we're being careful about. It may not be this flavor of thread safety for some people, and I'm not even suggesting that this is the best way to detect problems. What I am saying is that I have the power to create like a house style of what we want to be paranoid about and implement that house style. So if I go back into setup, right, here's that. What we do is, hey, we're only going to check this one file. We could check many files. We could have a list of what are the files that we want to check for thread safety. If we're in that file, we scan for external references. Now, scan for external references, like before, iterates over all the expressions in every declaration. If there's an identifier, we check it. If it's a struct dereference, we say that's fine because we'll catch an external reference in the name of the struct, so we don't care about that. If it's an import target, chase it to the source of the import. If it's a constant, we don't care if it's defined in another file because it's a constant. So like if you have the number 35 defined somewhere, I don't care where it's defined, it's thread safe if it's a constant literal. So that's fine. Now, if it's not in our file, in whatever file that we're scanning, then we have a whitelist, right? And that whitelist is somewhere here. And we can put this in a separate file for reasons well, I'll show in a bit. I reordered the order of what demos I was going to show. But I have a whitelist here where it's like, okay, these are the things that that file or any file is allowed to call. So there's like basic modules that we know we've audited, we know are safe. So like the thread library and the basic stuff for the compiler and the preload for the compiler, those are all safe. And then if it happens to be in the mixer, we know that that thing can call anything in cache decoder because, you know, the compressed audio decompressor lives there, and we can call the Win32 module, right? But anything else is bad news, right? We don't want this file calling out to anywhere else. So this is not completely foolproof, right? If you were to be outright antagonistic, you could subvert this mechanism. But most of the time, what's going to happen is accidental problems, and this will catch those accidental problems. Now, the other thing is, well, we'll talk about whitelists in a second in the next example, because the next example is pretty good too. Another very game-specific thing that's maybe a little more complex than this. Let's go back to our little space shooter game. Actually, let's go. I sort of factored this out into sort of the standard library engine right now. Let's go look at the structure of the entity manager for a second. This echoes the kind of structure I do in all my games lately, except it's a more performant version that uses structive arrays and stuff like that. But you've got some entity manager that hangs on to pointers of all the entities and manages creation and destruction of them. And it allocates things in batches. I demoed this in the structive array demos a long time ago. And then we've got entities where the base class is stored SOA, so that we have very good memory performance of that. And then we might have some derived classes, and those are going to be defined in our client program that inherit from this or whatever, and provide custom functionality, right? So here's the thing is, what we do in order to manage entity lifetimes is one of the few basic approaches that you can do that keeps you sane in an engine, right? What we do is we say, look, you're not allowed to hold a pointer to an entity across frames. You're supposed to hold the portable ID, right, which is one of these things. And then you ask the entity manager, give me a pointer to this, please. Anytime you want the pointer. And then the entity manager, if you want to destroy an entity, you call it to register a destruction, and at the end of the frame at a known time, the entity manager deletes all the entities, right, and calls cleanups on them at a known time in the frame and all that stuff. So you don't have like random weird things happening in the middle of the frame, right? So when you take an entity pointer, you can hold on to it for a little bit, like in your own function and anyone you call, but you're not supposed to store it anywhere, right? You're not supposed to keep it. And this is a very real problem that I had, actually. I've been working with this kind of system forever. I find it to be the simplest thing. I like it much better than some kind of reference counting weirdness that slows things down, and also, you have reference leak problems and all that kind of thing. This is a very hard, low overhead, simple way to do stuff. Now, someone new came on the team, actually several new people came on the team, and I usually explain them this kind of a thing because it's a house rule of our system, right? This is how our engine works. It's a thing you need to know. But then, someone was doing engine programming for like a year and didn't play with entities at all, and then a year later he goes and does entity programming and he forgets about this, right? And so he promptly stores entity pointers on an entity, and then those pointers get deleted out from under him, and you have that classic, oh, I'm pointing to deleted entity problem. So I programmed an example that catches that, right? So I can go to, we're in the other program now, so I'm going into first, and actually, let me go into entities, which is a file in invaders. This is where I define all my, it's a very simple game right now, so we've just got a bullet, we've got an invader, we've got a pickup, right? So say I'm the new programmer on the team and I want to add some information to bullets to optimize things or make things faster. So I want to store a pointer to who fired me, and if there's other bullets fired at the same time in my group, I'm going to store them in an array here, right? And so now if I try to compile this, it's going to complain. Boom. Hey, you got an error in struct bullet. You can't store any pointers on a struct. See our house wiki's code guidelines for a full explanation of what the problem is, right? So you can point people, because this is your code and not built into the compiler, right? You can point people to an external reference of what you did wrong. And so it's complaining about line 31, this very obvious reference to another entity. If I comment that out, it'll now complain about line 32, actually. This more involved, array of pointer to pointer thing. Now, this is very interesting to me. As I have a small company and think about growing it into a bigger company, right? Now, we almost had this capability before, right? If you watch the type info demo, you'll know that I had the ability to inspect the types in the program. But we only could have made it a runtime check, which is annoying, right? Because you have to run the program for the check to go off. And the reason we were only able to make it a runtime check is because there was never a time during compiler time when you knew that all the types in the program were complete, right? Anytime a hash run happened, maybe some more of the program would not have happened yet. But now that we have these specific workspaces delineating things into certain packages, and you get a message from the compiler, hey, the code is done being compiled and we're about to make the executable, that is a time to do something like this audit, right? Let me look at when this call gets called, right? When we get this complete message, audit for entity pointers, right? So now we have a well-defined time to look over all the type infos, and we actually get the type table from the workspace that we're operating on, not from our own workspace, right? We have our own type table of our own stuff. We iterate over that and we look for entity pointers in this very small amount of code. Now, what's interesting to me is, as I grow my company, I want to get away from bureaucracy, right? I want to be able to have people be maximally effective and just to be able to feel free and work on the code. And a lot of what happens when you onboard new people, especially into complicated code bases, is they'll make mistakes and they need to be shown the lay of the land by the more senior people. And the problem is that those more senior people's time is very valuable. So if they start spending all their time code reviewing new people's code, it's going to make them miserable, right? It's going to make your company feel more bureaucratic. And what I'm saying here is that with a structure like this, it becomes very easy to to automate a large class of this kind of check. You can put it into a continuous integration build or something like that. Then as soon as people compile, right, or check in their problem, well, hopefully before they check in their problem, you detect this stuff and you give them helpful links to the wiki or just descriptive errors, or you say, come talk to Bob about this specific thing, or send Bob an email so that you don't interrupt his train of thought, right? So I think this is a very, very handy thing to save senior people's time and help them remain sane. So there's a few things I want to reiterate. I want to go back over what we showed, right? We compiled multiple builds in parallel with different settings. We totally went bananas with this IDE-like thing. Let's show that again because it's so fun. Hopefully the music won't be too loud again. We showed this very interactive, nice IDE thing. It's not really a full IDE or anything, but it shows what you can do at compile time. And then we showed all these kind of very serious checks and augmentation you can do by iterating over your code. We translated our code to a different programming language. Let's do that again because that was so fun, right? I have all these options at my fingertips. It's very easy to make them go, right? I don't have to juggle a ton of weird make files in Ninja and Visual Studio. And all of this stuff is completely consistent across platforms. All of this works exactly the same because it's the same program. It's the same programming language, right? You don't have to have a lot of weird tools. You don't have to have a lot of weird build steps, right? And yet, all of this really high-level stuff that we have done, you know, some languages give you this sort of ability to inspect your program, but usually they're very high-level squishy languages. They're not languages that compile down to the same level as C, which we do, right? And we do all of this in a very simple way without having this extra compile time, const expr, crazy thing that is not as powerful and has a convoluted syntax and all that. No, we just do it. We just write code, right? The reason that I was able to write this go bananas thing very quickly is that, oh, I quit out of it. The reason I was able to write this very quickly is because it's just a regular, straightforward program of the kind that I write all the time. I didn't have to do some convoluted compile time thing. So that is what I had to demo today. Hopefully I wasn't too rambling. I didn't have as much time to prep as I usually would like due to being banned from Twitch today and having to start up a different channel. We'll take questions in a little bit. Hey, look, I'm jumping around my program again. Oh, let's do one last thing. I want to... There's sometimes junk files that get in here, but let's see how long the compiler is. Yeah, 21,321 lines. It's about this many files now to compile the whole... This is the whole compiler, right? And because it's in C++, this is about twice as many files as you would like because there's all these H files. So, you know, you'd like to have enough files to fit on one screen, and you could once we ported this into a different programming language. But it's still relatively small by compiler standards, and yet it does all this stuff that I showed you. And if you use your imagination, you can think about some relatively powerful things that you can do as a small jump from what I demoed today. I'm going to take a 5-minute voice break, and when I come back, we'll do questions and answers. Yeah, and in the meantime, we'll have some intermission music. So back in a minute. Well, okay. So we're going to do questions, and I saw the obvious question already, which is there going to be a time when you can modify the tree of the program? And the answer to that is yes. I just haven't gotten there yet. This already turns out to have been a big enough demo even without that, and I was blazing through things. I did not explain things at a very detailed level. Like I could have gone through the tree of like what all the syntax is, and we didn't do that. So I'm sorry if it was too fast. But yeah, I have not yet implemented the ability to modify the tree, but it'll be there. And we'll see what that looks like when it happens. I'll probably do it in a few steps because some things are easier and some things are harder. So I'm going to do the easier things first. Oh, someone's asking, can the compiler stuff look at comments? Right now, comments are invisible to things, mostly because I'm just not really sure where to put them. Maybe, maybe when you get a closed file message, you can do something like you can access all the comments as if they were strings or something. I don't know. It's interesting. I would like to, certainly if you're going to translate your program into another programming language, you would like to keep the comments, right? Now you could also do that like, because you get the file in line of every single thing, right? Like if there's a plus sign, you know what file line and character that plus operator happens on. So you could combine that with reading the text file around that to try and get the comments out, but it would be easier if it just gave them to you. So I think that would be good. Pseudonym 73 is asking, compare this with Clang, which is a set of libraries for parsing and manipulating C++ code. I mean, the thing about that is, it's a headache to even go there. Like, hardly anybody goes there, where they build a wholly separate utility that links to libclang and all that stuff. Like, even doing that is a giant headache. And then making sure that the build settings are the same is a headache. And then integrating that into your regular build process is dicey, because you have to make sure that exactly the same things are happening. What if you're not even using LLVM as your regular compiler, right? Like what if you're compiling on the Intel compiler because you want some optimizations that they do, right? Or if you're compiling the Visual Studio compiler because you're targeting the Xbox One, then all of a sudden you're trying to use two different compilers, and that's a disaster. So really this is about making it very easy and very accessible to do all these things. Does the compiler generate debug info? Well, certainly from what I showed, this is like all the debug info you could ever want, right? You actually could take everything, all this information, that I showed. For example, what was, I don't know, let's go back to the translate to scheme, right? For all of this, whoops, I defined it in the other order. Print expression, all these different expression node types, you have the whole program, right? So instead of outputting the program in a different language, you could output information about the program to any debugging format that you want, right? Now, I haven't implemented any of those natively yet because I'm sort of waiting on when we actually generate assembly code and stuff for that, because that's part of the interface with the debugger. But if you wanted to, today, you could just output the debug info for your program. You're not limited by the compiler in doing that. Someone asked about AST modification. I already answered that. Oh, will libraries be allowed? So that's the thing. Everything that I demoed today is sort of coordinated by the main program. And the question is, what access do libraries have? And that's a question of coordination that I just wanted to get this stuff in before I start asking about that, right? The question is, because if you write a library, you might want to be able to modify your own AST, and you might even want to be able to modify the AST of your caller if they use your data structures and you're doing interesting things. So that has to get worked out. We will just have to see. First, I want to get the basic modification ability in first. Someone's asking about workspaces again. How do you tell that the code is separate? If you do nothing by default, right, you can just do it exactly the way that I did in previous demos, and everything goes into one workspace and nothing is different. But let me go back to the game. Here, when we say start a workspace, what that does is it just calls this create workspace function. That just says, makes a new arena where it's like, I'm going to start throwing code in here, and everything in here goes into one program. And here's the file to start. Here's the path where all the files live. And, all this stuff down here is just me tracking the workspace on my own, right? And remember, we set the build options in this proc. So the reason I only add one file is because then the way that I happen to have laid this file, I could have added more than one. But here I've just, at the top of this file, I pull in a bunch of stuff. So that's where all the rest of the program comes from, right? So I just create a workspace and I add the files. As soon as I add files to this workspace, the compiler is going to start compiling them and then give me the messages about them. So this is really all you have to do. Then if I make a different workspace, like I do down here where I compile, debug, and release separately, if I make a different workspace, it's just a different, completely separate universe. Yeah, you need to import the compiler module for the definitions of this stuff. And that defines, let me fit this whole thing on screen. So this defines this stuff like create workspace, destroy workspace, begin and end intercept, wait for message. This stuff is unused right now, but I'm thinking like maybe you can reject code if it's for a different platform or something. If you want to parse it for stability reasons, but then you want to reject it or something. You can report an error and get the type table, both of which I did during the demo. And as I mentioned, maybe there's a way that you call the libraries, or maybe there's a way to arrange it so that the libraries see themselves as a main loop too. I haven't thought about that too hard. Any other questions? When you are doing the compile time code running with run, is there any guarantee on the compilation file order? So when you do run, you are guaranteed that everything required to run that run is compiled, right? As always, there's a very sophisticated dependency system running in the background, so the compiler knows what that depends on. However, as for other parts of the program, you don't have guarantees on whether those are compiled yet. They may be, they may not be. And I'm sort of I'm not going to freeze that implementation detail one way or the other yet because I'm not sure what is best. However, that's one reason why I wanted to implement this streaming model, right? So that you can see in what order things compile, and maybe you can tweak it and tune it even. One thing that I didn't demo, but that I could have, is that you could measure what time each of these messages comes in. So if some files are taking longer, or even some individual declarations in individual files are taking longer, you can measure the time on that and tell, at least pretty close. Actually, there shouldn't really be anything making noise there, aside from the fact that you're running multiple things in parallel. But if you really want timing, you probably turn off parallelism, right? So that someone else's workload isn't making you seem slow. So all that is doable, and I think it's actually very exciting. Now, the other thing that I did was I want to make it possible to sort of gate, you have like a fence or something, or I call it a stopper because fence is usually referred to, used to refer to threading primitives. So you could have a stopper in a file, and a run could like, you could be guaranteed that everything before the stopper runs and that nothing after the stopper runs until you release the stopper. The main reason for that is so you can pack a lot of code in one file like Sean does with the STB libraries, right? If you don't need to pack a lot of code into one file, then you know that this isn't compiled until after you add it. So I can do any kinds of zany processing that I want before I add this file, and I'm in strict control of when it happens. But if for simplicity of packaging you want to put all your files together in one, there's not yet a very strict way to control that, but there will be. Is the plan to continue this trend to the native code generation? Tell me when you're going to use inlining or sub-expression elimination, etc. Yes, I believe so. There's a question about maybe at some point are there too many messages and it slows you down, but then maybe you can turn off which messages you want to get, right? If messages are optional or you put them in certain categories like, oh, I only want, parsing messages, or I only want, bytecode messages, or I only want optimization messages. So I believe that that can be very, very, very useful. And that kind of graphical view that I showed at the beginning of like how big everything is, if you can pop up graphs for like what's inlined, that's great, right? That gives you a level of visibility into your program that nobody really has. And I think it'll be cool. What is the compile time penalty of using a custom build stage? I mean, it kind of depends on what you do with it. Right now, there's not that much of a penalty, I don't think. There is, we do copy out all that data, right? Like as soon as you say begin intercept, we need to start copying out data and feeding it to you. But I don't think that that's really very slow compared to the other things that happen during compilation. So, and we'll see though, right? I mean, it isn't even finalized what happens here. So in order to really answer that question, you need to have a big program with big libraries all doing this stuff, and then we can measure. So I don't know. But my design goal will be to not make it prohibitive to do this stuff. I think, for some of these crazy checks, like for example, in the MISRA recursion check, I built a call graph of my program, which is not a trivial operation. Maybe you only want to do that kind of heavyweight operation once in a while, right? And so maybe you have different variables on what kind of build you're doing, and maybe once a week you do the heavyweight checks or something. Or your continuous integration server does them every hour, but it's not something you, as a user at a computer, do. It's something that the machine in the back of the room does, right? So there are all sorts of ways to mitigate expense if it turns out to be a problem, but I don't even know if it will be. I don't have plans to convert assembly back into this language. I'm not sure why I would do that, but maybe someday. I don't have anything like public and private yet. There's going to need to be something like that. Like I don't yet have a namespace management that works very well, and we're going to do something like that eventually. It's just this kind of thing makes a language much more powerful, and then like something like public and private is more like a smaller organizational tool that is often misused actually. So I don't want to dive too far into that. I'm not going to get into the garbage collection discussion that I feel like is happening in chat. Someone said generating a 200 millisecond HTML page. Dude, 200 milliseconds is really slow. If you're taking that long to generate a web page, I probably don't like your site. Are closures coming soon? I don't know. I'm going to do the rest of this stuff first. Like I'm going to do modifying the AST, and then I'm going to do polymorphic data structures, and then I don't know. We'll see what's on the roadmap after that. Could you compile in the compiler? Well, you certainly could write a compiler for this language that you run at compile time right now. I have not done that. The compiler is still in C++. So, that's not something that I do, but if you really want to inception yourself, you could do that. It's not a priority. All right, last couple of questions before I go. I've been sitting here a while. Will I publish my version control? Maybe, I don't know. I don't think that's super important, but as an educational tool, maybe. Yes, we have function overloading. I demoed that, actually. You can go on YouTube and see that. Can this be used to report global scope functions that have only a single reference? Absolutely. Like, you mean like you just want to detect, oh, this is just a useless wrapper and you should get rid of the wrapper or something? Yes. If that's your house style, you can trivially do that, actually. Do I still have annotations? And if so, are they in the AST? Yes, I do, and yes, they are. They're on struct members right now. I don't think I export them yet for random global declarations, but I will. That'll be in that declaration struct. Any plans for algebraic data types? I don't know specifically what you mean about algebraic data types. I mean, that could mean a few different things. And I'm not that pedantic when it comes to functional languages, so I don't tend to think that overly mathematically formalizing your data type system has been very productive, aside from limited domains, like theorem-proving kinds of languages. If you're not making a theorem-proving language, I'm not sure that that's really worth it. Does the next compiler for this language need to maintain compatibility of compiler innards? Is that part of the definition of the language? No. I'm taking great pains to insulate people from implementation choices. Now, I may not be completely successful in that, and we'll see. So there may be a few things that have to carry over, but for the most part, no. Like all these data structures exposed in the AST, like I said, are exposed via a mapping. They're not the same as the internal data structures. So all that can change. However, what I also want to do is have a DirectX style model for this language where the language is allowed to evolve in a backward incompatible way. We'll see, like why, without making people grumpy about that. I think as long as the benefit to that is big enough, people will want to upgrade their code. And if you provide them a compiler that still compiles the old code, then they'll be happy with that too. That's a totally different issue though. And I want to get a good base language before I worry about that stuff. Okay, I gotta go. Thank you everybody for coming by. At least part of this will show up on YouTube. Hopefully the rest of it will. I'm gonna see what Hitbox says about whether my whole video is recorded and whether I can upload it and stuff. Or download it and edit it. So thank you for hanging out. Thanks for the good questions. And we'll see. We'll see when I have another demo for you. It's very erratic because we're in this difficult time on the witness when we've got to get a lot done so we can launch. So I may not be working on this for a little bit. We will see. Good night, everybody. Have a good time.